In 2023, one European carrier watched a third of its fleet stop flying. The order was not an emergency. It came from the manufacturer. Ground the aircraft, pull the engines, ship them out, and wait. That wait would stretch past 250 days per engine against an industry norm closer to 75. Nothing had broken. Nothing had burned. Nothing had fallen from the sky. Pratt Whitney had built the most efficient commercial engine of its generation, a genuine engineering triumph, and airlines were now parking it by the hundred. The reason why reveals how modern aviation really works. Behold the PW1100G-JM, the engine at the heart of Pratt & Whitney's geared turbofan family. 2 decades in development, more than $10 billion spent before a single revenue passenger boarded. It is not a refinement of an existing design. It is an architectural break from how commercial jet engines had been built for half a century. Here is the principle, stripped to its essentials. In a conventional turbofan, the fan and the low-pressure turbine are bolted to the same shaft. They must spin at the same speed, but they want different speeds. The fan wants to turn slowly. The turbine wants to turn fast. For 50 years, engineers accepted the compromise. Pratt & Whitney refused. They inserted a reduction gearbox between them, roughly 3-to-1, and let each component finally spin at its own correct speed. The payoff was extraordinary, roughly 16% lower fuel burn than the previous generation. A noise footprint cut by around 75%. Reduced emissions across every measured category. In an industry where a single percentage point of fuel efficiency can decide which manufacturer wins a fleet order worth billions, these were not incremental gains. They were a generational leap. The engineering press called it the most significant propulsion advance in decades. But Pratt & Whitney was not alone on the wing. On the same Airbus A320neo airframe sat the LEAP 1A, built by CFM International, the joint venture between General Electric and Francis Safran. The LEAP was the conservative choice, conventional architecture, no gearbox. Decades of shared DNA with the CFM56, the most widely produced commercial engine in aviation history. Airlines choosing between them faced a genuine decision, and the logic was not sentimental. Fuel is the largest controllable cost line an airline carries. Nothing else moves the margin further. So they gambled. Indigo, Lufthansa, Spirit, Wizz Air, JetBlue, Hawaiian, dozens of carriers across every continent committed their fleet plans to the geared turbofan. Thousands of engines ordered. Entire route networks designed around fuel numbers that only this engine could deliver. And in the air, the promise held. Operators confirmed the savings were real. The gamble had paid off, which is exactly what makes the next part so difficult to comprehend. Now, the geared turbofan did have a troubled entry into service. This is documented, and it matters. From 2016 onward, operators reported combustor liner distress, premature oil seal wear, and prolonged startup times. Carriers flying in hot, dusty environments suffered worst. India's aviation regulator grounded aircraft. Airbus deliveries slipped. Pratt & Whitney issued fix after fix, redesigned parts, absorbed the reputational damage, and slowly worked the reliability curve upward. By the early 2020s, the worst of it appeared to be behind them. Engineers had solved the problem they could see, but none of that is what parked hundreds of aircraft in the desert. Not the seals, not the combustors, not the dust. The catastrophe that arrived in 2023 had nothing to do with any of it. July 25th, 2023. RTX Corporation, the parent company of Pratt & Whitney, held a routine quarterly earnings call. Analysts expected the usual: delivery figures, margin guidance, supply chain commentary. Instead, Chief Executive Greg Hayes delivered a disclosure that would reorder fleet plans on 4 continents. A manufacturing condition had been identified in a component deep inside the engine core. It was not confined to a single batch. It was not confined to a single year. It spanned an entire production window, and every affected engine would have to come off the wing. The market understood immediately. RTX shares fell sharply within hours, erasing tens of billions in value in a single session. Airline executives began calling Hartford before the call had ended. Lessors started auditing their portfolios. Nobody yet knew the full number, but everyone in the industry understood the shape of what was coming. And here is what made it unlike anything the industry had faced before. This was not a design flaw. The architecture was sound, the gearbox worked, the fuel numbers were real, the engineering, the part that had taken 20 years and consumed more than $10 billion, was fundamentally correct. What had gone wrong sat further upstream, in a process most people outside aerospace have never heard of, involving a material most passengers have never considered. Pratt Whitney had not built a bad engine. Pratt Whitney had built an excellent engine around a material that should never have passed inspection. The distinction may sound academic. It is anything but. One of those problems can be fixed with a software update or a redesigned part. The other requires opening every single engine, removing components that cannot be repaired, and scrapping them. There are no shortcuts here. Here is the mechanism, in plain terms. Certain high-pressure turbine discs and compressor components are not machined from a solid billet. They are built from powder metal, a nickel alloy reduced to fine particles, then compacted and forged under extreme pressure into a single dense part. The process produces components with superior strength at temperatures that would destroy conventional forgings, but it depends entirely on the purity of the powder. Between roughly 2015 and 2021, powder produced at a Pratt & Whitney facility in Georgia was contaminated. Microscopic inclusions were introduced during production and sealed inside the finished parts. Those inclusions are the problem. Under the thermal and rotational loads inside a running engine, an inclusion can seed a crack. The crack propagates. Given enough cycles, the component can fail. And a high-pressure turbine disc failing at operating speed is not a contained event. Now understand why this was so much worse than a normal defect. The contamination is statistical, not visible. There is no external symptom. A borescope inspection finds nothing. A pre-flight walk-around finds nothing. Engine health monitoring data looks entirely normal. The affected engines were flying beautifully, delivering exactly the fuel savings promised, right up until the day the manufacturer announced that some unknown fraction of them contained a flaw that could not be detected from the outside. The scope emerged in stages, and each stage was worse. Roughly 1,200 engines required accelerated removal and inspection within the first year. The wider affected population climbed toward 3,000 engines. RTX took a charge against earnings of approximately $3 billion. Pratt & Whitney's partners in the international consortium absorbed further losses. Airbus, which had built its narrowbody delivery ramp around this engine, watched its customers begin cutting capacity. The problem faces three devastating constraints, and none of them can be engineered away quickly. Constraint number 1, the inspection mathematics. There is no way to check an affected engine while it hangs on the wing. The engine must be removed, shipped to a specialized facility, and completely disassembled. The high-pressure turbine and compressor discs must be extracted and subjected to ultrasonic inspection and detailed lifing analysis part by part, serial number by serial number. Discs that fail assessment are not repaired. They cannot be repaired. Contamination is intrinsic to the metal itself. They are scrapped, and replacements must be manufactured from scratch using the same production capacity already stretched to its limit, building new engines. Consider the arithmetic. Thousands of engines, each requiring full teardown, each requiring parts that do not yet exist. Every replacement disc that goes into a grounded engine is a disc that cannot go into a new one. Airbus deliveries slow. New aircraft arrive without engines. The problem feeds itself. Constraint number 2, shop capacity. The global maintenance, repair, and overhaul network was never designed for a simultaneous fleet-wide teardown. It was sized for the ordinary rhythm of aviation, engines coming off wing on a predictable schedule spread across years. That entire assumption collapsed overnight. The numbers are brutal. A normal shop visit for this engine family runs somewhere near 75 days. Under the powder metal recall, turnaround times stretched past 250 days, and some operators reported waits approaching 300. That is not a delay. That is an aircraft removed from service for the better part of a year, while its lease payments continue. Pratt & Whitney added capacity, qualified additional facilities, ran shops around the clock. it was not enough. The spare engine pool, the buffer that keeps airlines flying through routine maintenance, was consumed within months and never recovered. At the peak, more than 600 A320neo family aircraft sat grounded worldwide, wings stripped, waiting. Indigo alone parked roughly 70 aircraft. Wizz Air grounded around 45. Lufthansa, Spirit, Hawaiian, JetBlue, all absorbing the same wound in proportion to how deeply they had committed. Compare this to how the industry normally recovers from a crisis. The 737 MAX grounding, catastrophic as it was, ended with certification of a revised flight control system, a software fix, validated and deployed fleet-wide. The Rolls-Royce Trent 1000 blade durability problem, which parked Dreamliners for years, was ultimately solved with redesigned blades. Both were engineering solutions to engineering problems. This is different. There is no fix to certify. There is no software patch, no redesigned component that resolves the fleet. The metal already inside those engines is compromised, and the only remedy is to find it, cut it out, and replace it, one disc at a time, across thousands of engines, using industrial capacity that does not exist in sufficient quantity anywhere on Earth. Constraint number 3, the money. Somebody has to absorb the cost of an aircraft that cannot fly, and the contracts governing that question were never written for an event of this scale. Pratt Whitney negotiated compensation agreements with affected operators, and those agreements are substantial. But compensation is not restoration. An airline does not lose only the value of the engine. It loses the summer. It loses the routes it had already sold, the crews it had already hired, the slots it had already paid for. Wet leasing replacement capacity at spot rates during peak season is punishing, and every carrier hunting for substitute aircraft at once drove those rates higher still. Meanwhile, the lessors kept collecting. An aircraft parked in the desert with its engines in a shop in Texas still generates a lease payment. The rent does not pause because the metal cannot fly. For carriers with heavily leased fleets, this was the cruelest arithmetic in the entire crisis, paying full price for assets producing nothing. The casualties arrived quickly. Spirit Airlines, already financially fragile, watched dozens of aircraft go idle at precisely the moment it needed every seat flying. The grounding was not the sole cause of its bankruptcy filing, but it removed the margin the airline needed to survive. Wizz Air abandoned entire markets, closing its Abu Dhabi operation and cutting routes across its network. Indigo, the largest operator of the type in the world, leased older aircraft back into service simply to hold its schedule together. Now consider the comparison that defines this crisis. In the years the geared turbofan spent building its reputation, Airbus was delivering roughly 600 A320 family aircraft annually. At the peak of the recall, more than 600 of those same aircraft sat grounded. An entire year of global narrowbody production parked, not obsolete, not damaged, not old, simply waiting for a part. Pratt & Whitney projected recovery through 2024 into 2025, then extended it. The current expectation reaches toward the end of the decade before the affected population is fully cleared. That date has already moved more than once, and every operator planning against it now builds in margin for it moving again. None of this analysis suggests the geared turbofan should be dismissed. The architecture was never the villain. The gearbox works exactly as designed. The fuel savings are real and have been confirmed in service by operators across every climate and route structure on Earth. Airbus continues to sell the engine. Airlines continue to order it. Pratt & Whitney's core engineering judgment that separating fan and turbine speeds would unlock a generational efficiency gain has been vindicated by the very aircraft that were grounded. Every major manufacturer is now studying geared architectures for the next generation. The engine was right. What failed was industrial, not conceptual. A powder production process in a single facility over a 6-year window introduced contamination measured in microns, and that contamination propagated outward until it grounded a tenth of the world's newest narrow-body fleet and pushed an airline into bankruptcy court. This is what modern aerospace has built for itself. Extreme specialization concentrated in very few hands. One supplier, one process, one material, and hundreds of airframes hanging on it. The efficiency that makes these supply chains possible is the same efficiency that leaves no absorption capacity when something goes wrong. There is no reserve, there is no slack. The system runs at exactly the tolerance required and not one unit more. The question was never whether Pratt & Whitney could build the world's most efficient engine. They did. The question is whether an industry engineered to this degree of tightness can survive being surprised even once.